Welcome to Lecture 1. In this lecture, I will provide some basic introduction to brain-computer interfaces, also known as, in short, BCI, or brain-computer interface systems. The outline of today's lecture is as follows. First, we'll try to answer the question, what is BCI, or brain-computer interface? And we'll go through the different components of the BCI, and we will see how it works, and also we will see how and why it is difficult to build a brain-computer interface system. And later, yes, we will summarize important topics, challenges of BCI research. And we will see different components of the BCI system. Let's take a look at some of the Hollywood movies that highlight the BCI, the brain-computer interface, in their science fiction movies. So humans have already fantasized to build some connection to the brain or to read human mind. Well, in these examples of these posters of the movie, we see that we have some kind of exoskeleton robot that is connected to the human brain, and then there is a direct control of these exoskeletons coming from the brain. So even here, for instance, in this movie, this movie really very interesting. I recommend you to watch, which highlights the science fiction and the idealized form of the brain-computer interface. Also, we can call these systems as neural interfaces. We have some system implanted or connected to the human brain, and then the exoskeleton. And also, probably this is a little bit older movie, but also shows the example of controlling human avatar from home remotely by just thinking. Another example and the other example. Well, these Hollywood movies reflect the idealized form of brain-computer, also known as brain-machine interfaces, we can imagine. So there is a human, and with their brain, they're trying to control either computer applications or some external devices, such as exoskeleton, robot, or some remote controlled avatars. Important question in BCI research is it even possible to build such systems? Can we hope to have these kind of systems in the future, or is it just being hyped? Let's take a look at different components of the idealized BCI, brain-computer interface systems, in those Hollywood movies. So what we have is, we have the brain, human brain, and we have some external computer applications, or the computer itself, some connection, control, and then the brain involves thought. And in those idealized science fiction BCI, they are very fast and then accurate. Fast in terms of translating human thought into control application. So you can control exoskeleton very fast and with very high precision and accuracy. And also we can see what the other characteristics of science fiction BCI is as psychic, natural, intuitive thought directly turned into action. Right? So it's just like very, very natural and intuitive. You just think, and then your thought will be decoded into control signals, and then you can use those control signals to control those external applications. So, so we have feedback, some virtual reality, okay, maybe um, the movie Matrix, right? Also involves some kind of description of science fiction BCI. We also see physical connection to central nervous system. So central nervous system is entire brain, right? Plus some nervous connection. So they have physical connection. Well, another thing is that the better than natural or human. So that's a question. So all of these characteristics of science fiction BCI, brain-computer interface, is it better than natural human interaction? Is there a two-way communication? Is two-way communication possible between computers and the brain? So we can have two different settings here. The first is brain-computer interface versus computer-brain interface. So in brain-computer interface, what we have is we have human brain connected to external device, and the communication goes in one direction, from brain to outside device. So brain puts information into computer or some other device. So in CBI case, so computer brain interface case, we have external device. This can be a computer that is putting information into your brain, right? So there are two possible ways. So there are some brain disease disorders such as Parkinson's disease. They, for instance, use some so-called neurostimulation to stimulate certain parts of the brain, and we can think of this kind of stimulation as putting some information into the brain. Also, there are also some other brain disease conditions such as epilepsy. In practice, we can see CPI systems being used in clinical areas. So the aim is to stimulate certain parts of the brain to disrupt or to change the way the neural connections in the brain work. One of the early applications of computer to brain interfacing, it can be given in these examples. So for instance, we can use CBI to remotely control animals. Or even there have been some attempts to get some to restore human vision using bionic eyes for blind people. And deep brain stimulation, as I briefly mentioned, is in practice nowadays for treatment of Parkinson's disease or even for depression. In one of the remote controlled animals, example has been done by University of California, Berkeley, Professor Mahar Bees. So what they have tried to do is to control this beetle, okay, the green June beetle, by electrically stimulating the nerves, okay, wing nerves of this beetle. So they could control the speed and then the direction of the flight of these green June beetles. And another example is so bionic eyes. So we have some digital camera, right, acquiring the images of surroundings, and then those images is being translated into some electrical pulses, right? That stimulates certain part of the um, area of the brain that is responsible for vision, so visual cortex, also so called. While these are early examples of CBI's computer-brain interface, there has been a lot of recent advances as well. Nonetheless, our topic in this course is we focus on building brain-computer interfaces, as in the following example. I'll show you a couple of demonstrations of a BCI or brain-machine interface that has been developed by researchers. In the first example, we will see a paralyzed woman controlling a robotic arm with her mind using the most advanced brain-machine interface ever developed. She can steer a robotic arm towards a bottle, pick it up, and drink her morning coffee. In the other example of brain-machine interface system is shown here. This is again the earlier work that has been published in Nature Journal. So we see a person paralyzed, totally paralyzed. He has the implanted electrode and he can control the cursor using these thoughts. This is one of the very important application of brain-machine interfaces for paralyzed people. While we will study the differences of brain-machine interfaces, the one which you have seen corresponds to invasive form of brain-machine interfaces. You can see here a tiny electrode that has been implanted on human brain cortex, as shown here. This is the result of the project, so-called brain gate project. So this is, we have a gate to the brain, and those tiny electrodes are controlled to the motor cortex of the human subject, and these are basically the signals coming out of the brain, and they are being translated in real time to control a computer cursor or external robotic arm. In this example, we see a brain-machine interface that is based on non-invasive approach. So, as you can see, a participant or this subject has electrodes, electrode caps picking up brain signals in a non-invasive manner from outside the brain, from the outside the scalp. Let's see. So what we have here is brain signals are being recorded in real time and being decoded into control commands. So basically, grasping. This also shows one of the important or essential application of brain-machine interface, brain-computer interfaces to support people who may have some amputated limbs. And we can see here usefulness of this technology. So the brain-machine interface, along with robotic research, can help us to restore the motor function of the people who may have paralysis or who have lost their motor functions using some external prosthetic arms. Let's take a look at the other example of the non-invasive brain-machine interface that can be used to control a robotic device. So this is a little bit early work we have done in our lab at Nazarbayev University a few years ago. The task is very similar to the one we have seen. Let me just pause here. So you can see different components. We have a human subject, which is me, and there is some cap, like swim cap, like put on a scalp with sensors attached. You can maybe you cannot see these sensors, and the task is to record, measure brain activities that correspond to mental intent of this participant and translate it into control commands. Those control commands can be move up, left, right, forward, backwards, and then we also have the gripper here. Maybe it just can be used to grasp the bottle. So let's quickly take a look how it looks like. So one of the things that I want to mention here that the non-invasive brain-machine interface systems or brain-computer interface systems are less accurate, much slower than the invasive brain-machine interfaces, as you can see here. However, they represent one of the safest interfaces we can develop to assist people who may need such technology. Okay, so let's take a look. And this is one of the very raw video, not professional, taken from one of our experiment by a student. So you can see a little bit shaking, shaky camera, shaky image. Yeah. All right. So it took around a few minutes to perform these tasks. So in reality, building the brain-computer interfaces can be challenging. You have seen a couple of video demonstrations, all look good and accurate, in particular the so-called the brain gate project that we have seen can be used for controlling the cursor in two dimensions or the external robotic arm to reach grasp objects or some other application. We also have some portable technology, portable system that allows us to record brain signals in real time and then control, let's say, a computer application. This is a game. Or other applications such as grasping the bottle. We will see the BCIs or BMIs can be used also in virtual reality applications or for spelling. So for people who are unable to communicate, we can try to develop technology using BCIs. So now, if we compare the reality to the hype, or we can see that the control of the external devices using brain-computer interface is much less fine-grained. So it is not easy as in those, let's say, science fiction movies, or even those demonstrative videos. And also we need to emphasize that in reality, BCIs are restricted to only a small set of options, just few commands, right? And also they're very slow and inaccurate. One character, okay, much less. So, and also non-intuitive. So your thinking is not literally being translated into control signals, but you have to develop different thinking strategy so that you can control external robotic arm using your brain activities. And also we see that the signal that we record from the brain signals are corrupted by different source of noise. As a result, we got some low signal to noise ratio. So the point here is again, in reality, the BCIs, building a brain-machine interface or brain-computer interface systems, are challenging, requires a lot of engineering tasks that we will review in the upcoming lecture. Also note, please, that I use BCI, BMI, or brain-computer interface, brain-machine interfaces interchangeably. Right? So there are some minor differences in the way they're formed, but they mean the same technology, same system. So I can switch brain-computer interface to brain-machine interfaces during these lectures. Okay. Also, they are called sometimes neural interfaces. Look more closely how BCI systems may work. So, what is BCI, or brain-computer interface, or brain-machine interface? So we have some common definitions that can be used. So one of them is, it's a system which allows someone to communicate information about their mental state without the use of peripheral nervous system. So there are two components that I want to emphasize. So we have mental state, we have someone, okay, and then peripheral nervous system. So without the use of peripheral nervous system is one of the important things. So the information, okay, should come directly from the brain, right? This means, yeah, again, we need to record brain activities only to convert into control. So peripheral nervous system means no muscles, no eyes, no motor neurons, nothing outside the skull. How does a BCI work? So it is fundamentally a simple engineering problem. We can put different parts, components of the entire system in 4 different parts. So here, for instance, we can take a look at the entire flow. We have generation, okay, which involves getting the person to produce strong brain signal, either by performing an explicit mental task or through normal mental process. Right, so first is we need to get the data out of the brain or brain of the person or participant. So he should generate strong signals by thinking, right, a specific mental task. Second, since we have this data being generated by the person, we have the measurement part. So we need a system, some kind of technology, some sensors that will pick up the data or the signal or the brain signal from the human participant and then provides us quantifiable data of some form. So there are different technologies that we can use for measuring brain activities. fMRI, functional magnetic resonance imaging, EEG, electroencephalography, or MEG, magnetoencephalography. There are some other imaging modalities that we can use to record brain activities, but these are just examples, 3 commonly used ones. And once we have the measurement, which provides us data, the next step is, next part of the BCI system is a decoding. So decoding involves building a classifier or decoder or machine that can decode the data that has been recorded, and that corresponds to mental intent, mental state, mental intention of the participant, right? To infer, again, mental state of the participant so that we can use it to output some control signals, control or communication signals. In this case, the communicate With, for instance, computer application, it could be translated as moving the cursor in XYZ directions or to generate a control signal to move the robot arm in some given direction. And finally, we have the feedback. So the person generates a brain signal, okay, that corresponds to his or her mental state, mental intent. The device picks up that signal, quantifies, gives us discrete data. The set of machine algorithms, it's a computer algorithm, will decode that data and convert or translate it into control signal. And then person needs to see the result of his or her intent, either in a visual form or as a form of sound, auditory form. Basically, these are the let's four different components of the BCI. As you can see, looks not that complicated. This is also we can call it as BMI system. In the coming lectures, we will stop by and delve into each different components of the BCI system in detail. For instance, we will see how brain signals can be generated using different experimental paradigms. We'll also take a look at different measuring modalities such as EEG, MEG, and fMRI. We can also take a look at the decoding. And the most interesting part of this BCI system could be this part, decoding, using sophisticated machine learning algorithms that allows us to decode human mental intent. And finally, we'll discuss the potential applications of the decoded signal in as the output to communicate, all right, with the external world or to control some sort of device. Again, why we care about the design BCI? In the first place, we want to, or the BCI researchers want to help people with severe motor paralysis who are unable to walk, to move their upper limbs or lower limbs, or to communicate.